So can you see the screen?
Yes, sir.
Okay. Okay, welcome to week 6 of this particular NPTEL live session. So this course is deep learning and provided by Professor Pravir Kumar Viswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. And today we'll actually be solving week 4 quiz, for which you've been already graded, and as well as we'll take up some some questions regarding week 6. So let's dive into the quiz part first. So let us take the first question. So the question states that what is the main benefit of stacking multiple layers of neuron in a nonlinear activation function over a single layer perceptron? So So can any one of you tell me that whether A is correct or not? And just not about the yes or no, please give me the reason as well. That if A is the correct option, then why? And if it is the other way around, then also what is the reasoning behind that? Yes, anyone?
Sir, that is not correct because if the multi layers will be there, in between their hidden layers will be there, and the complexity will increase more during the propagation.
Yes, actually during both back propagation and forward propagation as well. For example, if you have a multi-layer perceptron like this, let's say you have two hidden layers, H1 and H2. H1 and H2, and this is your input and this is your output, Y. So now you can see to get Y, let's say over here the weight is W1, over here the weight is W2, and here weight is W3. So to get Y, first you have to, let us consider there is the activation function is linear. Okay, so there is no sigmoid or ReLU any kind of thing. So we have linear activation in each of the neurons present in the what you call the layers, hidden layers, or in the output layer as well. Okay, so first thing that will happen is W3 into H2. Then H2 will come from H1, so W3 into W2 into H1, and then W3, W2, and H1 comes from W1 multiplied with X1. So obviously there will be a transpose sign based on from which direction you are doing the multiplication, and therefore you can see while propagating the input to the output layer, you can see the number of multiplication will increase as you increase the number of hidden layers. Therefore, this is the forward propagation. Forward propagation means in which you provide the input. Input will be passed through these cascaded hidden layers, and subsequently it will produce the output, that is Y. Now, if you increase the number of hidden layers, that means the weight in between these layers will increase. And if the weights are, if the number of weights are increasing, that means you have to perform the multiplication and addition operation that you have to perform to get the output. That will also subsequently increase. Therefore, if you use multi-layer perceptron, it increases the computational complexity. And the option says just the opposite thing, that it reduces complexity, which is incorrect. Okay. Now, the second option is reduces inference time during testing. Now you can see, let us consider you have trained a multi-layer perceptron model. Now at the time of testing, what you will have to do, you need to get Y. Now you can see if the number of layers number of hidden layers have been increased, that means you need to increase the number of multiplication and addition operations. So here I have considered only multiplication. I have considered that there is no bias. So bias term associates addition operation as well. So let us consider there is no bias. So therefore the operations are like this. Now you can see that uh, with increase in the hidden layers, as the operations number of multiplication and number of addition increases, which is analogous to the inference time. That means let us consider you have a very small problem at hand. So therefore, if the problem needs very less calculation, that means it can be solved in faster manner. At the same time, if you have been given a very big problem and it requires lots of calculations, so therefore it takes time to get to the answer. So that is the analogy of this particular option. So if your number of hidden layers have been increased, that means mathematical operations have been increased, and as it will also increase the inference time. So therefore, it does not reduce the inference time, rather it increases. So therefore, option B is also the incorrect one. Okay, so the third option says that it allows to create complex nonlinear decision boundaries. So you can see that, for example, in case of XOR gate, you have seen that if you have two features x1 and x2, the features looks like this. So over here you got one class, there is another one. So now you can see this is not a linearly separable problem. So for the nonlinear, so this is basically a nonlinear separable case. So there, for example, you cannot put any decision boundary which is line. By putting a straight line, you cannot bifurcate these two classes. So you need some kind of nonlinear boundary. So to solve these non-linearly separable problems, we basically stack the number of hidden layers, because we hope that if we put the number of hidden layers followed by nonlinear activation in the hidden layer, the features may get transformed into some another domain, which can make this problem, this non-linearly separable problem, into a linearly separable problem. So that is why if you have seen the XOR gate uh, implementation using a multi-layer perceptron, you would see that, one second. Yeah, so you would see that instead of having single layer, there you have two layer. So one layer, to get an XOR operation, you need OR operation. Here you need a NAND operation, and here you need an AND operation. So out of these operations, this is x1, this is x2, and you have an associated bias over here. And over here also you have a bias over here. So you can see initially the AND gate and OR gate problems, which were solvable using a single layer or a single neuron. Rather, in case of an XOR gate, as the problem itself is not a linearly separable problem, we need two layers of neurons. So this is the input layer, and this is the second layer. So therefore, by stacking multiple layers of neuron, what we try to think is that in the intermediate layer, the outputs will be transformed into another domain in which the problem will become a linearly separable problem. So therefore, option C is correct. Okay. So the second question is quite related with the first one. So you can see over here that for a two-class classification problem, what is the minimum number of nodes required for the output layer of an multi-layer neural network? So what is going to be the correct answer for this? Is anyone?
One.
One.
And why? Why?
Because we can do 0 or 1 classification using one node.
Yeah. So if you have a single output neuron, so you can put in the output layer, you can put a sigmoid function. So the sigmoid function will map the intermediate output into either 0 or 1. So therefore, if you have a sigmoid kind of activation over here in the neuron, so you just by using a sigmoid function, you can get either 0 or 1. So therefore, that is the reason, which is why the minimum number of neuron in the last layer for a two class classification could be 1 itself. Okay.
Sir,
Okay.
can you
Just
go back to the previous question?
yes.
Yeah. Sir, when will be the situation we will get the two output layers? Like how
Yeah. So,
many, it should be what classification problem?
so for example, okay, 1 second. Yeah. So for example, if the problem is like this. Let's say, uh, for example, in this case, let's say this is case 1. In this case, you have cat versus dog classification. So this is two class classification. So using a sigmoid function, you can generate either 0 or 1. So let us consider cat class is 0 and dog class is 1. But let us consider you have another classification. For example, in case of case 2, you need to classify cat versus dog versus cow. So in this particular classification task, you can see that you have three outputs. Now, in case of multi-class classification, you have seen we use the function called softmax. What softmax basically gives is the probability of occurrence to a particular class. So for example, this is your input layer. You have some hidden layers over here. And in the last layer, in which the classification will be done. So in the last layer, you will have three set of neurons. So for example, if you want to classify cat, as because softmax gives you probability. So let's say cat class is the 0th class, dog class is the first class, and cow class is the second class. So if the image which you are feeding as an input, that basically belongs to cat. So for the cat class, you will get high probability, let's say 0.9. And as the image is belonging to a cat class, so for other classes, the probability will be very small, let's say 0.05, and over here also 0.05. And as because softmax gives you a probability, so total probability will be equal to 1. If you add all these things, you will get 1. So therefore, in case of multi-class classification, so this is binary classification, as because you have two classes where you can just generate 0 or 1. However, in case of multi-class setting, multi-class classification, there you require more than one neurons. For example, if you have three classes, then you need three neurons, because you need to get three probability values to get to know that given an image, that image belongs to which particular class. So over here, let's say the image is belonging to cat. So for cat class, you can see that the 0th neuron is having highest probability. So you will decide that, okay, the image is correctly classified as cat class. So in case of multi-class classification, you require more than one output neuron.
Then, sir, when the option 2 will be holds good then? Sorry, option number 1, that is 2.
Option number 1. So over here, you can see that minimum it is mentioned. So you can generate, let's say, let me take another page. So let's say you have cat dog classification. For instance, you have a binary classification. So this is your input layer, this is your hidden layer, and this is your output layer. Let's say you have two neurons. So this belongs to, let's say, dog class, and this belongs to cat class. And the image belongs to dog class. So you can use over here, let's say you can use softmax function again. So for example, if you use softmax function over here also you will get two probability values. Let's say if the image is belonging to dog class and if your model is performing very well, then it has to give correct classification that the image belongs to dog class. So over here your softmax output will be again high, let's say 0.9. And as because this is a dog class, it is not the cat class, so probability for cat will be low. So over here you can see that the problem which was there in case of binary classification, you can you can get the final answer using only single neuron, as well as you can get the answer using two neurons, as because you have two classes. But as because they have mentioned that minimum number of neuron, so for to get minimum number of neuron, that means you just need to generate either it belongs to 0th class or it belongs to the first class. So therefore, to get either 0 or 1 representation, we use sigmoid function. So therefore, the answer will be 1, as because it is written that minimum number of nodes required. You can use both sigmoid function and softmax function. You can use both sigmoid or softmax function. So if you use softmax function, as it will give you the probability values as an output, so you need two neurons. However, if you are using sigmoid function, there you just need one neuron. And as the problem states that minimum number of neurons required, so we have to consider that we are using sigmoid function, which will give me either 0 or 1, and hence we require only one neuron at the output.
Okay, sir, got it. Thank you.
Okay.
Hello.
Yes, yes.
Sir, is there any difference between feed forward neural network and multi-layer perceptron? What is the difference between both two? Feed forward neural network and perceptron.
They are basically the same. They are basically the same. So multi-layer neural network means you have a stack of hidden layers. For example, for instance, let us take two cases. One is this is single hidden layer, and there is a input layer and there is a output layer. Same over here. So this is the output and this is the input. So this is a shallow neural network. Shallow neural network. And this is basically the multi-layer version, as because you can see that there are stack of subsequently you can see that there are stack of layers have been introduced in between the input and output layer. And whereas in this particular case you can see that there is only one hidden layer. So this is very shallow network. So both these network basically use the concept of feed forward mechanism. So feed forward mechanism means that if you have an image or if you have an input data, so you feed that input data and the input data will be propagated in the forward direction to get the output. So this particular mechanism, feed forward mechanism, is applicable for each and every neural network. So for example, over here you can see that if the image is represented by X, so to get output Y, you need to pass the image in the forward direction, as well as if you if you feed an image over here in this particular network, so there also you have to pass the image in the forward direction to get the output, that is Y. So feed forward means that you are just feeding the input in the forward direction of the model to get the output. So that is a mechanism. So this feed forward mechanism is applicable for both shallow neural network and multilayer perceptron. So multilayer perceptron, it becomes when you increase the number of hidden layers in between the input and output layer. Other than that, every feed forward model or multilayer perceptron, they are just the same.
Okay, sir. Thank you.
Okay, so this is the third question. So they have given two inputs x1 and x2, and this is the bias corresponding to the first layer or the input layer. Okay, along with that, they have given that what is the value of x1 and x2. So x1 is 0 and x2 is 1 over here. And this is the first hidden layer and this is the output layer. And the nonlinearity basically represented over here, which follows these kind of functionality. So this is basically the zero thresholding. If value is greater or equal to 0, then it will be 1, other else it will be 0. And we need to find what is the value of A3. Fine. So A3 is equals to a nonlinear function of, let's say I can write it as minus 0.5, or let's say let me use the feed forward mechanism over here. So feed forward mechanism means I need to pass the input in the forward direction. So let us first try to get the output at this particular location and at this particular location. So for A1, the output will be 0.5 into 1 plus minus 1 into 0, and then you have 1 into minus 1. Okay, so it is 0.5 minus 1, so minus 0.5. As well as at the output of A1, you have the nonlinear function. So f of A1 is equals to f of minus 0.5, which is equal to 0. So that means the output from this particular node is 0. So I'm writing the value over here. Similarly, the output at A2 is basically f of A2. So I can write it as f of. So A2 is what? 1 multiplied with minus 1.5. That means minus 1.5. Then 0 is multiplied with the weight 1. So that is 0. And again, 1 is multiplied with the weight 1. Okay. So f is minus 0.5 over here. And again, the value will be 0. Okay, so now at A3, the output is minus 0.5 into 1. This is corresponding to the bias term. Then you have 0 multiplied with 1. So it will be 0. And here also the value is 0 multiplied with 1. So output is 0. So therefore at A3, the value is 0.5. And again, you can see that output of A3 is basically nonlinear activation applied on the summation, the linear combination. So this is f of minus 0.5. So therefore the output is equal to 0. So here we have seen that how the feed forward mechanism works. So if the feed forward in the feed forward mechanism, you provide an input and the input will be passed in the subsequent layers to produce the output. And it will travel till the output layer to find the final result of the neural network. So over here, this is the final layer of this neural network. So we need to pass the input in the subsequent layers to get the value of A3. Okay.
Sir, one doubt.
Yes.
But For A1, A2, we are getting the answer. We have to check with thresholding zero thresholding condition. After that only we have to use as a input to A3 as well.
Sorry. After thresholding, yes, after thresholding,
Yes.
after thresholding, you have to use that value to the
Use.
input. Yes, yes.
Okay,
Because what
okay.
is happening is that, let me show you the basic structure of any multilayer perceptron. Let us consider this is a neuron of a multilayer perceptron. So what it does is, let's say this is weight 1 and weight 2. Let me consider you have just, let's say, till weight 5, or let me generalize till weight n. So it will give you the textbook version. So x1, x2 and xn, and you have a bias term 1 and the bias value is b. So the neuron, first what it does is actually it generates a intermediate value y. So y is nothing but a linear combination of all these weights and input values. So this is wi xi plus b. So that means if I just expand it, you can see the multiplication w1 x1 plus w2 x2 dot dot till wn xn and 1 into b. So that will give you the bias term. So this I have just represented over here in the summation format. Now after you do this particular summation, then what it happens is that you apply a activation function. Activation. So that activation, let us consider the activation function is represented as f, and that is the output of the neural network. So output of the neural network is f of y, that is f of wi xi plus b. So this is the fundamental structure of any neuron of a multilayer perceptron. So that means first you have to do the linear combination. That is what we are doing. And then you have to apply the nonlinear activation, and then you can pass it to the next layer. Is it
Okay,
okay?
sir, I understood. Thank you. Yes, sir, thank you.
Okay. Okay, so another question is that you have this particular neural network architecture. So here also, by this particular question, the previous question that you have asked, so that can be answered again. For example, if I just start writing the equation for this particular neural architecture, what it does actually, first it generates an intermediate representation y, and then it incorporates a nonlinear activation, and then it generates the output p hat. So I can write it as y is equals to w1 x1 plus w2 x2 plus w3 x3 plus 1 into b, that is the contribution of bias, and the p hat will be generated after you apply the nonlinear activation. So that is fnl of y. So that means first you do the linear combination, and then you feed that linear combination output to the nonlinear activation, and then you will get the final output of any neuron, which you can subsequently pass to the next layer. Okay, fine. So the loss function is p hat minus p square, and they have asked to find the derivative with respect to w1. So that is del j del w1. So for these kind of problems, we need to we need to follow the chain rule to get to the derivative done. So we can see that J is basically made up of P, or P hat rather. So let me just expand this. So J is P hat minus P. So you can see that J is made up of P hat, and P value is already target value that will be given, but the variable quantity that it has is basically this P hat. So that means J is dependent on P hat. So I cannot directly take derivative of J with respect to W1. Rather, we need to go through the chain rule process. So first the J will be we need to take derivative of J with respect to P hat. Then you can see that P hat is made up of Y. So del P hat of Y, and then you can see Y is made up of W1. So now you can take del Y by del W1. So in this way, you need to go for the chain rule process, because you can see that J is made up of P hat is made up of Y, and Y is subsequently made up of W1. So that is what we have followed over here. Del J divided by P hat, then P hat divided by Y, and then Y is divided with respect to W1. Okay. And in the question, they have said that this nonlinear activation function is a sigmoid function. So effectively, P hat is equals to sigma of Y. Okay. So now we just need to evaluate these derivative values. That's it. So del J by del W1. So the derivative of J with respect to P hat will be, sorry, there is a square over here. So derivative of J with respect to P hat will be what? It will be 2 into P hat minus P. Then what we have is that we have to take derivative of P hat with respect to Y. So we can see that P hat is basically sigma of Y. And what is the derivative of sigmoid function? What is the derivative of sigmoid function? We did it in the week 1 quiz.
1 by 1 plus e to the power minus
1 by 1 plus e to the power minus x. So probably that there is a specific form is there. So you can see that you cannot
Sigma
see
y
that.
into 1 minus sigma y.
Yeah. So that is sigma y into 1 minus sigma y.
Sir, how this form comes, sir?
Okay, then let me do the derivative first. So let's say you have sigma of x. So what is the formula of sigma of x? That is 1 plus e to the power
1 plus e to the minus.
minus x. Now what we are doing is that we are doing sigma dash of x. We are basically trying to find the derivative of sigma with respect to x. So that is dtx of sigma x. Okay, so it is 1 plus e to the power minus x whole square, and then 1. So you guys do the derivative part and tell me what is the final answer. So you will get a form, but that will not be the final form. We need to do some manipulation. So what is the final answer? Just tell me after doing this particular derivative part.
It is minus e to the power minus x divided by 1 plus e to the power minus x whole square.
Yeah, so minus e to the power
Minus
x divided by
1 plus e
e
to
to
the
the
power
power
minus
minus
x
x
whole square.
whole square. Fine. So let me just do some algebraic manipulation over here. So you can see that I am dividing this part into two subsequent parts. 1 plus e to the power minus x. So now you can see that what sigma x is this one. So sigma x is coming back. So you write sigma x over here. And 1 minus sigma x is equal to 1 minus 1 divided by e to the power minus x over here. So you can see that probably you have done some mistake.
Sir, it will be e to the not minus e to the power minus
Yes, yes. So there will be
I
no minus.
minus.
So 1 minus sigma x is 1 plus e to the power minus x minus 1 divided by 1 plus e to the power minus x. So 1 will cancel with each other. So you'll see that this is e to the power minus x divided by 1 plus e to the power minus x. So you are getting 1 minus sigma of x. So now you can see if you take the derivative of sigma x, so you will get this form. Sigma x into 1 minus sigma x. So here we are doing the same. Instead of y, instead of x, we are having y. So you are taking the derivative of sigmoid function. So like what you have got over here, we are writing the same here. Any confusion?
Understood, sir. Clear.
Okay. So this part you can see that we have done this one. We are done with this one as well. Now we have del y by del w1. Now del y by del w1, what it will give is that uh, it will give you x1 and rest of the things it will consider as constant values. So derivative will be 0. So let us just check. So this is the answer 2 p hat minus p sigma of y 1 minus sigma of y multiplied with x1. So this is the final answer.
Sir, excuse me, sir. In the lecture video, the half is multiplied to remove the 2, but here
Yes.
it,
So this is basically the question. They have formed it like this. It is not like this is the rule of thumb that you can put a half factor to remove this particular 2. But in question, they can even write like this p hat minus p cube. So to form a question, they can put anything. But in conventional technique, they put a half to scale down this to what is coming over here. So in mathematical problem, they can put any sort of function. Instead of 2,
okay.
they can put 4 as well. Anything they can put. Even, for example, this is a squared loss. You can see this is a squared loss. So there is a square over here. They can give. So this loss is called L2 loss. L2 loss. So probably in KNN lecture week, you had seen that Manhattan distance. So that is basically an L1 loss. So they can write p hat minus p as well. Okay, so they can put anything and then they will change this neural operator and then you have to calculate the derivatives accordingly. So for as far as the question is being concerned, they can put anything in the question.
Okay, sir.
Sir,
Got it.
sir, what is the difference between this neural network and the previously which we have seen?
This is not a neural network. This is just a neuron of a neural network, just a single neuron. So this is a single neuron. But what we have seen over here, this you can see, this you can say that this is a full version of a neural network. It has an input layer, it has a hidden layer. So this is input layer, this is over here, this is the hidden layer, and this is the output layer. So this whole thing creates the neural network. But in this particular question, we are just looking at a particular neuron. For example, like this one. We are just looking at a particular neuron. However, so let's say this is question 3, and This is question 4. So in question 4, we are just looking at the single neuron. However, in question 2, we are looking at the full neural network architecture. So that means in question 4, we are just looking at this particular neuron rather than looking at the whole thing.
Okay, sir.
But the mechanism is same. Whatever network you've been given, the mechanism is same. So the mechanism is like this only. First you do the linear combination, that is x1 into w1, x2 into w2, like that. Then you pass it through a nonlinear activation and subsequently you will get the output. So this process is same with whatever neural network that you've been given over here in this week quiz at least.
Sir, now in this particular neuron, the Y will be the last output, right, sir, which will come at A3.
Yeah, yeah.
Yeah, and now the network which you have shown there, it is P and P cap. So P is the target and P cap is nothing but Y.
Yeah, P cap is nothing but Y.
Okay.
P is the target one, that is let's say either 0 or 1. For example, you have given the cat or dog classification. So let's say if I tell you in terms of physical realization, let's say you have a neural network, this particular thing, and A3 is the final output. So you have this, and after you pass this particular image over here in this particular neural network, this is the final output. What is A3? That is equal to Y, you can consider, or you can consider it is P hat. And you have seen that in case of classification problem, you basically given with an input image and its label, that is P, that is the target. This is what is target, and this is the input image. So now your target is to produce P, but you are producing P hat. So there should be a finite loss in between these two. So that is why you are calculating the P hat minus P whole square, or half into P hat minus P whole square. So that is thing.
Okay, sir.
Sir, if it is labeled and the already classification is over, no, then why we should like here X is the given the feature and the P is the target. It has been mentioned that it belongs to which class. Then why we go for then again classification?
Okay, for example, we are human, we are intelligent enough to, uh, for example, when we were child, and when we were started learning, so we had we need to train our brain. So to train our brain, our parents would have seen, would show that okay, this is a image of cat, and then we got to know this is a cat. So that means at the time of let's say when we started learning the things, then our brain weights were uh, the weights were very much sparsified, and then we started learning it. So to learn something, first we need some guidance. So to guide something, our parents would have tell me that okay, if this image is given, so this is a cat image. So to train any particular model, first we need some label data, and after your brain is trained, now eventually if you see a cat is passing by, so for that particular instance you can see that okay, my brain is trained and now I am intelligent enough to say that, to classify it as a cat image. So therefore at the time of training of the model, when the model is, let's say, a dumb model, it is not able to predict anything, for that we need training labels. And once the model is trained, now we need to show it some unknown image to see that whether your model is performing well or not. So at the time of training, we need the target. However, at the time of testing, we are not required with the target, your target level. So for that time, for the real time instance, we need to feed an image of cat. I know that image is cat itself, but you need to see what is the prediction of the model. If the model predicts it's cat, then you can see that, you can say that your model is performing well. And if not, then your model is a dumb model again. So for the training purpose, we need the target values. And once training is done, then we don't need the target values. You show in an unknown image and the model will be able to classify.
Okay, sir. That means we are preparing the model to in the
To
learning
learn,
stage.
yeah, in the learning stage, to prepare the model, we need target. Because we need someone, for example, we need a teacher to teach mathematics, mathematical problems. So what is there in the textbook? And if my learning is well, when teacher is teaching me, if my learning is well, in the final examination, I will be able to classify the the the
Sir, you're not audible.
uh, I think in between the internet connection was not well from my side.
Yeah.
So what I was telling is that, let's say we need a teacher to teach us. Okay, so let's say we are learning mathematics. So the teacher has a textbook. Now from the textbook, he is teaching us mathematics. So he is solving some numerical problems, and by that we are learning those things. Now in the examination, in the final examination paper, obviously you will see some problems which you have never seen in the textbook. So that is the test data. Now if my training or my learning process is very well, then only I will be able to solve these particular questions, and I can infer, okay, this problem is related to that particular chapter, and then this is the process I should have to proceed with to get the final answer. So that means at the training time, I need some target values. So for that, the learning to get the learning mechanism done, so we need the label data. At the testing time, obviously you'll be seeing some unknown data which you have not seen in the training time. And if you are able to classify that particular image, then your model is performing well. Otherwise, it's a garbage.
Okay, sir. Thank you.
Okay, so this question states that you have find the output p hat. Yeah, Sumit has raised his hand, I think. Do you have any question?
Hello.
Yes.
Sir, if our model is classified perfectly, then there is no need of updation. Then what next? Our model is perfect.
Okay, if your model is perfect, for example, uh, let's say I can give some examples from my research area. I'm working in biomedical signal processing. So in our area, what is our aim is basically you have some diseases. Let's say, let me take an example of an ECG signal. So if a normal person is there, his or her ECG will look like this. So this is a normal ECG bit. So, and this is quasi-periodic. So because heart is pumping continuously, so you can see this kind of pattern. And let's say and this is an abnormal case. So this is an abnormal case. Now, let's say this is cardiac arrest. and this is normal or healthy. Now you're trying to train a machine learning or deep learning model to classify into two classes, either normal or unhealthy, or whatever the disease pathology you have given. So that is the final target. Now, given this model, if you are getting, let's say, 95% accuracy or something, so your question is that what is the next thing that we can do? So next, what we can do is that if your model is perfectly working well, you can deploy it in real time. So you can make a miniaturized device in which your deep learning model will be deployed into a embedded processor, and you can create a pipeline like this. So let's say this is an MCU microcontroller over which you have deployed your deep learning model. So this is called deploy operation. And then in the real time, you have a human over here, and you can collect the ECG signal, let's say from these three node points. So in real time, you will get signals like this. You can feed the signal and you can get the final output. So let's say either normal or unhealthy. And you can these kind of miniaturized devices are called point of care medical device. And this is the final pipeline that you can do. Otherwise, another option that you can do, you are getting 95% accuracy. You can you can investigate that why 95, why not 99. So that means you need to check that for which of the cases your model is not performing well. There is some confusion. That means there is still a 5% confusion is there that your model is giving incorrect classification. So you need to check that what is the parameter by which you can further increase the model accuracy. There are several applications are also there. So this application probably in uh, Shark Tank season 1, there was a company called Spandan. So they had created something like this. So they had probably deployed any deep learning model into a microcontroller. They were collecting the ECG signals and then they were processing it, and they were showing that whether the signal is belonging to a normal class or an unhealthy class. So you can create some device out of that.
So, sir, our final is aim is to create to get the 100% accuracy
See, 100%
or
accuracy,
close to 100%.
yeah, close to 100%. That means your aim should be, you should get high accuracy. With 100% accuracy, there are still some problems are there. For example, your model could be biased. There are some issues are there with absolute 100% accuracy. Uh, the model which achieves that level of accuracy. So it is always preferred that you should reach a substantial amount of accuracy. 95% accuracy is also very well, because finitely in real time, it is very difficult to get 100% accuracy at with the real time data. For example, in MNIST, I will show you in the next week. So we have seen that MNIST database is there, MNIST, which comprises the handwritten digits of 0 to 9, and will be classifying these handwritten digits using the multi-layer perceptron model. So there you will see within 10 to 20 epochs, the model reaches around 99% accuracy. So, however, in real time, you will see that maybe it will happen that the way I write 0, for example, I write 0 like this. The model has not seen anything like this in the training data set. So it has some, there will be some probability that the model may misclassify it. Or let's say I write 4 like this, and in the test time, I write 4 like this. So the model may be confused between whether this is a 4 or 9. Even though the model is giving 99% accuracy, at the test time, if I generate an image like this, so it may so happen that your model is predicting it as 9 plus, but I am writing it as a 4. So there is still some room is there for misclassification. So there are several components are there that has to be looked after before deploying the models in real time, apart from getting the 100% accuracy and all. So there are several aspects are there. Probably those aspects probably will not be discussed in this course, because this course is a foundational course for this is basically a get to know course about deep learning applications and the theoretical aspects.
So, sir, if we are getting 100% accuracy, then there may be a chances that our model is there is some problem in our model.
There is some problem in a model. Basically, what I mean is that in let's say you have trained a model. You have trained a model. I will be inferring to the biomedical data only. What happens in biomedical data, I will be referring to that. Let's say second. Okay, so uh, so you can see this signal is written as heart sound signal. Okay, so this heart sound signal, this is a normal heart sound signal. We can see that this is a normal PCG signal. PCG is basically known as heart sound. It is the full form is basically phonocardiogram. So the heart sound signal in case of a normal person, it looks like this. Now let's say you have, you can see that in between S1 and S2, let's say, let me take another example which has more clear representation. Yeah, this could be fine. This. So you can see aortic stenosis normal. So this you can see this is a normal heart sound. And you can see that in between these two peaks, intermediate values are almost zero. That means the signal is very clean. And you have trained your model to classify either normal or abnormal case, right? Now you can see in case of normal, intermediate values are almost equal to zero. However, in case of abnormal, you can see that there are some perturbations in between the larger peaks. So you can see the in between the larger peaks, there are no perturbations. You can see in case of abnormal, this mitral stenosis is a kind of heart attack. This is not kind of a heart attack. It basically refers to a valve disorder. So you can see in between the larger peaks, you can see that perturbations are there. Now you have trained your model using this particular data set where the normal signal is very clean. In between these two peaks, there is nothing. Now at the test time, let's say this particular data comes. Your model was giving 100% accuracy at the time of training. Now at the time of testing, you have collected a phonocardiogram signal from a real-time patient. Let's say you have collected phonocardiogram signal from me, and then you are feeding that particular signal to your trained model, which is giving 100% accuracy at the time of training. So you will see, you can see that in case of my phonocardiogram signal, intermediate values have some perturbations. Someone's mic is on. So the intermediate values, you can see that there are perturbations are there, but your model had not seen that in case of normal signals also uh, the intermediate values could be something other than 0. So your model may see that, okay, intermediate values are not 0, therefore it could be a abnormality. So it can map it to abnormal heart sound signal. So that means even though your model was performing very well in the training data, at the real time test scenario, your model is not performing well. So you need to check all these aspects. So that means even though you are getting 100% accuracy, obviously you have to check several aspects to get it deployed in the real time scenario. So this is one such example. For example, over here also you can see the normal signal they have given intermediate. There are several perturbations are there. However, you have trained your model with very clean PCG signal. So at that particular case, your model will be failed to classify the signal, and hence you can see that there could be a severe misalarming condition can be created. So you need to check back all these conditions before deploying the model in real time. So even though your model is performing very well in the data set, clean data set, but at the time of testing, your model may fail to recognize the correct class. So you need to check back all these conditions.
Okay, sir. Thank you.
Okay. So we were doing this particular problem. So in this problem, what we have is need to find the output p hat corresponding to these sort of values have been given and weights are also given, and the activation function is sigmoid. So p hat is nothing but sigmoid of this y. So I'm directly writing y as w1 x1 w2 x2 w2 x2 plus w3 x3 plus b. So sigma of W1 is 2 into 1. So 2 plus 1 into minus 1, that means minus 1. Then W3 into X3, W3 into X3 will be how much? 0 plus B will be minus 1. So sigmoid of 0. So what is the value of sigmoid of 0?
0.5.
0.5.
Yeah, so this is 0.5. So if I draw the graph, so at 0 it is like this, and as you increase the value, it is basically saturated to 1, and at negative side it gets saturated to 0. So this is the final answer. Okay. Okay, so this is the next question. We need to find del J by del W2, where the J is represented as a L2 loss and the target value have been given. Original target value is given P equals to 1 over here, and the nonlinearity is FNL is to be a sigmoid function. Okay, and then what you need to find is basically del J by del W2. So let us first write the equations for the output. So output is sigma of y. Y is W1 x1, W2 x2, W3 x3 plus b, and J is p hat minus p whole square. So I can write the del J by del W2. So what will be the chain rule? Del J divided by what?
Del P.
Del P hat, because P is given. So we are actually trying to extract P hat. So P hat is the variable and P is a constant value that have been given as 1. And then del P hat by
Del Y.
del Y, and then del Y divided by del Y by del W2.
Del,
Because you can see that Y is made up of W2. So Y can be differentiated with respect to W2. Okay. So now let us just try to see the corresponding equation. So this will be simply 2 into P hat minus P. And then what we have seen is that we are taking the derivative of P with respect to Y. That means we are taking the derivative of this sigmoid function. Sigmoid function's derivative is sigma Y into 1 minus sigma Y. Okay. And then what we have is over here del Y by del W2. That means output will be X2. Fine. Now we just need to evaluate all these values. So can anyone tell me that what is the value of P hat? What is the value of P hat?
0.
0.5. 0, yeah.
What is the value of P hat?
0.5.
0.5. As because we just have solved in the previous question, you can see that P hat is 0.5 and the values are same, I guess. 110. So we have 110 and the weight values are 2, minus 1, 1 and minus 1. 2, minus 1, 1, minus 1. Yes. So the output P hat is 0. Fine. Even this sigma of Y is basically P hat only. So I can even write it as 2 minus P hat minus P, then P hat 1 minus P hat into X2 del J by del W2. So this is the final equation. Now we just need to put the values. So 2 multiplied with half minus original target value is 1. So half minus 1. Then we have half, 1 minus half again, and we have X2. So X2 value is 1. Fine. So 2 into minus half into half, half. Okay. So over here we have minus 1 by 4. So minus 0.25. So this is the final answer. Any confusion?
No, sir.
Okay. So option D is the correct one. So now over here in the next question, it is basically the continuation of the previous question itself. So they have given what will be the updated value of W2 after the first iteration. So what is the gradient descent formula? What is the gradient descent formula for W2? What we can write?
W minus eta P hat
W2n minus eta.
P hat
Sorry.
P hat
Eta multiplied with what?
P hat
P hat.
1 minus p hat
1 minus p hat
into p hat minus pi p
into p
into
hat.
x2.
No,
minus
no.
p.
So you first tell me what is the gradient descent equation. Don't go to the final answer at once.
Dou J by dou W.
Yeah. So del J divided by del W2. So this is the equation of gradient descent rule. Now let us proceed to. So we have been told what will be the value at the first iteration. So n is equals to 0. So that means W1 at iteration 1 will be W0 minus eta into del J by del W2. So this is the equation. So now let us find what is W2 of superscript of 1. So W20 value is what they have given, that what is the value of W2 over here, that is -1. Fine. Eta value is 2 and del J by del W2 we just have evaluated. Del J by del W2 it is minus 0.25 minus 1/4. So it is -1 plus half. So value is minus 0.5. So over here option A. Any confusion?
No, sir.
Okay. Okay, the next question says that suppose you have a neural network has 3 inputs X, Y, Z. There are 2 neurons Q and F, and Q have been given as this particular form where Q operates X plus Y and F operates Q into Z. What is the gradient of F with respect to X, Y, Z? Assume X, Y, Z equal to these values. Okay, so we can write Q is equals to X plus Y and F is equals to Q into Z. And what we have to do is basically we need to take derivative of F with respect to X, Y, Z respectively. Del F, del Y, del F, del Z. What happened? So there was a problem with this pen. So divided by del Z. So let us start with this one, del F by del Z. So you can just directly see that F is dependent on Q into Z. So if you take the derivative with respect to Z, Q will come out. Then if you take del F by del Y, so can you see that whether directly you can take differentiation with respect to Y? Can you directly take differentiation of Y F with respect to Y?
Yes, sir. You substitute q as the x plus y, then we can
Yeah, so
substitute.
yeah, but the thing is that you need to think in terms of chain rule. Because if you see in terms of functionality, what you are doing is you are replacing it some by this one, but think it in terms of neural network. In neural network, you've been given the outputs and you've been told to take the derivative at the input neuron. So that is why they have written that your input layer has 3 neurons X, Y, Z. You have some hidden representation, you have an output where you have the neurons Q and F. Now you have to take differentiation of f with respect to the inputs. So that means you have to go by chain rule. So even though your approach is okay, but try to think in terms of neural network perspective. That in case of neural network, you have to go for the chain rule based application.
Dou f by tau q by tau x.
Yeah.
Like that.
Yeah, like that you have to do. Like that you have to
Okay,
do.
okay, sir.
So let us write it like this. So you can see that you cannot just directly write in terms of del y. So to write in terms of del y, you have to go through the chain rule. So del f divided by del q over here, and q is made up of y. So you can write del q divided by del y. Likewise, you can see that x component is not there. However, q is a function of x. That means you can start with this particular chain rule, that is del f by del q, and then del q divided by del x. Now from this, what will come at this particular derivative, you will get z. Again here you will get z, and here you can see that with respect to 1, that means 1 over here, and again over here you will get 1. So z value is what? Z value is -4. In the question they have given these values of x, y, z. So z is -4, and q is x plus y. So -2 plus 5 equal to 3. So your final answer will be -4, -4, 3. So option B satisfies this option. -4, -4, 3. Okay. So next question states that suppose you have a fully connected neural network has a single hidden layer. So you have a single hidden layer over here, which has 15 nodes, and the input is a 5-dimensional feature vector. That means you have 5 values over here. So that means 5 nodes, and number of classes. That means at the classification side, number of classes equals to 3. So you'll have 3 nodes. Calculate the number of parameters of the network considering that there is no bias. So there is no bias component. So that means additional components can be discarded. So you need to find total number of parameters. That means if you have a W1 weight over here, and if you have W2 weight over here, how many number of elements that is W1 and W2 both contains. So parameter. So what will be this first? Can you tell me what will be the size of W1? What will be the shape of W1? Size of W1? Yes, anyone?
So 5 into 15, so
Yeah, so
15 notes.
5 into 15. That means uh, uh, you have 5 rows and 15 columns, and similarly over here, what will be the size of W2?
15 into 3.
15 into 3. That means 15 rows and 3 columns corresponding to that. So total number of elements in case of W1, total elements in W1 will be how much?
75.
Yeah, 75. And similarly, yeah, and similarly, total
45.
number of weight over here is 45. So see, the final total parameter will be equal to 120. So option D is the correct option. So would have been the considered that the bias terms were included. So the number of parameters will change according to that, but they have considered the number of biases are equal to 0, as because they have said that no bias is required to construct this particular model. So you don't have to think about the bias terms. Okay. So another one question we have left over here. Yes. So in this particular question, they have said that you have two inputs over here, that is x1 and x2, and you need to check what is this whole neural network, what sort of logic gate can be implemented by this whole network. So what was your approach to solve this particular question? What was your approach to solve this question? So how many of you actually got this question but correct? How many of you got this particular question correct? This logic gate implementation for this particular neural network. And how did you do it? Anyone? Your approach basically, how did you go for this particular question? What was your approach?
NAND function.
NAND. NAND cannot be the answer. You can see NAND is also, it is not there in the list as well.
No, the
Answer
input
is C, sir. XNOR, sir.
for A1 output,
Yeah,
it will be
for
like an AND operation.
yeah, no, I'm saying that you have to check that you need to basically validate the truth table. Okay, so you have input 0 0 0 1 1 0 1 1 over here, and then given these inputs, you need to track the output. That means this is your x1, this is your x2, and for all these logic combinations, you need to check what is the output value A3, and then only you can say that what kind of logic gate has been implemented over here. So how did you do this particular mathematical operation?
Finding the output at each node.
Each
A1.
node? Yeah, that means you have taken a single combination, you have feed it through this particular model, and then you took the output, right? Like this.
Yeah.
Yeah. So that could be one solution. But last day, probably someone was raising question regarding if we can feed the whole data at the same time, and probably she was not getting the answer. So today I thought of doing that kind of solution. For example, we will feed this whole thing into this model, and then we will check what will be the output at A3. And then we can take up that what is the final result and whether we can infer it from the model or not. So to do that, we first need to write. So let's say this is weight 1 and this is weight 2. So how you can write weight 1? So you have been given the connection weights. So how can you write the weight 1? What will be the writing style of weight 1? So you can write it as like this. For example, first neuron in the second layer or in the hidden layer is A1. So you can see that what are the connection weights corresponding to A1. So you can stack them together 0.5, -1 and -1. Secondly, you have the connection weights for this particular neuron. So over here, this is -1.5, 1 and 1. Okay, so this is W1. Similarly, the W2 will be, you just have one neuron at the output. So you have three connection weights only. So you can write it like this 0.5, 1 and 1. Fine. Okay. Now, at the same time, when you have to feed the data into this particular deep learning model or MLPNN model, you need to do these operations. That is W transpose into X followed by this particular nonlinear activation. So let us start doing this whole thing for this particular layer, for this layer. So how can we write the X, the input? So how can we write the input? Incorporating the bias term.
1 0 0.
Yeah. So 1 0 0. And as I am considering that I will take the whole data and I will feed this whole thing into this model. So let me consider all 4 cases. So first case is 1 0 0. 1 is for the bias. Second case is again 1 because 1 is for bias. So second one is 0 1. So over here this is 0 1. Then you have 1 1 0, and again this one is for the bias, and this is 1 and 1. So this basically is bias. This one is x1 and this one is x2. So we have written whole combinations in this particular matrix. Now let us feed this whole matrix over here. So the shape of this matrix is,
But
you
sir,
can
x1
see.
and x2 values are not given right here.
So that is, you have to check. So they have the question is that what kind of logic gate it is there in this particular whole neural network. Now for a 2-input case, you know that for 2-input case, how many combinations you can write? 2 to the power n, that is 4 cases. Now how many 4 cases you can write using 2 logic operations? So these are 0 0 0 1 1 0 1 1. So for all these cases you need to check the output, and if you get the output, then only you can say that what is the logic gate operation have been performed over here. So given the input, you need to
No,
check
sir,
the
my
output
question is,
first. Yes.
no, sir, my question is the matrix which you have written, right? So there
Yeah.
1 1 is a fixed, like, or we can write there 0 0 0. In that way we have to write.
Oh, so you are asking about the order.
Yes, sir.
You're
Yes,
asked.
sir.
So you can change the order. That is not an issue. You just have to see that for 0 0 operation. So in whatever manner you write, you just need to check that, okay, so I was feeding 0 1 at the first instance. So for 0 1, what is the output? You just need to track it down. So to track it down in a orderly fashion, I have written in this particular manner because the conventional way to write the logic operations are like this only. So that is why I have written like this. You can change the order, but you need to track it down. For example, if you consider that, let's say you put as 0 1 and you got a output like 1 over here. But at the inference time, you thought that, okay, for 0 0 our output is 1. So this can give you misinterpretation. So to avoid that, I have just written it like this in an orderly fashion. Otherwise, you can feed anything, but you need to care about that this logic correspondence are correctly written. So 0 0 0 1 1 0 1 1. This particular order is just to mean that the output I can able to track it out at the output side.
Okay, then even we can write this is vertically also, sir, like bias is in a first column.
Yeah. That you can write. That you can write. Even you can write it like this also. For example, 0 0 1. That is also you can write. If you are writing 0 0 1 in case of X, that means bias is at the last part. So over here, then the weight representation will be -1 and then 0.5. You have to cautious about this part also. If you are changing your writing style over here in X, you have to change your writing style in the weights as well, because you can see that this first 0.5 weight connection is for bias. So you have to change your writing style in case of W2 as well. So they have to correspond with each other. Otherwise that W1x1 plus W2x2 thing will not occur. Got it?
Okay, sir, got it.
So the main thing is that whatever convention is given in the question paper, try to stick to that. Otherwise, if you are changing the order or doing something else, you should be cautious about all the framing styles. For example, if you change the order of x1, the way you write x1, if you are putting the inputs above and then at the end you are putting bias, you need to change the writing style in the weights as well. That you have to be cautious about. Okay, so over here the shape is 3 cross 4 and your weight 1 is you can see this is 3 cross 2. So we'll be transposing this whole thing. So after transpose, it will look like 0.5 -1 -1, then -1.5 1 1. So now you can see that it is of shape 2 cross 3, and then you multiply it with 1 1 1 1 0 0 0 1 1 0 1 1. So what will be the output of matrix multiplication? What will be the output of the matrix multiplication? The output will be of shape 2 cross 4. So please find the output of the matrix multiplication. So what will be the first element over here?
0.5.
0.5. What will be the second element? So you multiply like this. So
Minus
0.5. Yeah, minus 0.5. So minus
Third one
0.5.
0.
So third one is
0.
not
Sorry.
0.
No.
Minus 0.5 again. So you have 0.5 into 1 and then minus 1 into 1. So you will have 0.5 minus 1. So hence minus 0.5. Okay. So the
Minus
fourth
1.5.
one, yeah, minus 1.5. Okay. In the second case, what will be the output?
Minus
So first one is
1.5.
minus 1.5. Second one is
0.
0.
Minus 0.5.
Yeah, minus 0.5. Then again
Third
you
one is
will be
minus 0.5.
minus 0.5. And last one is
0.5. 0.5.
0.5. So
yes,
this is correct. So if I use sigmoid function for all these values, what will be the output? Because sigmoid of 0.5 is what?
0.
Uh, sorry, over here the function is given over here. So this is not sigmoid, this is f. They have given the function f.
Conditions.
So they have given the condition. So the condition is if the output value is greater than equal to 0, the output will be equal to 1. So over here you can see the value is 0.5. So that means output will be 1. Okay.
1 0 0.
1 0 0 0. Final
0
one will be
0
also
1.
0 0
0 0
0
0 1.
1. Yeah. So now you can see that you have 2 neurons in the second layer. So you are getting two outputs. A1, A2, A1, A2, A1, A2, A1, A2. So this A1, A2 is for this particular case, second one corresponding to this particular case, third one corresponds to this one, like that. So this particular row is A1, this particular row is A2. Fine. So let us go for the next phase. So we have got to this particular part. Now, if I try to extract the value of A3, if I try to extract the value of A3, now we have to consider this bias part as well, what we had did in the earlier case. So now we need to consider this bias part as well. So our input matrix will be of this sort: bias term, then A1, then A2. So for each case, bias value is 1. And A1 and A2 value we just have calculated. So for the first case, it is 1, 0. So this is 1, 0. In the second and third case, this is 0, 0, 0, 0. This is 0, 0, 0, 0. And in the last case, this is 0, 0, 1. So this is 0, 1. So this basically represent this particular thing. And now we need, so let me rename it as H. And now we need the weight values. So this weight value will come from this one. So this weight, I can write it as minus 0.5, 1 and 1. Okay, so this has a size of 3 cross 4 over here, and this is a size of 3 cross 1. And A3, you can see that A3 will give you a single value, right? Now let us consider the multiplication. So f of W transpose into H. So f of what is the W? If I take transpose, it will be minus 0.5, 1, 1. So and the H is 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1. Okay. So what will be the matrix multiplication output? What will be the
0.5.
shape? Acha. Okay, so this is 0.5.
Second
Then
one
second
minus
one
0.5,
minus 0.5,
minus 0.5,
minus 0.5.
0.5.
Yeah, so 0.5. And now you do the nonlinear activation over here. So what will be the final output? Final output will be
1, 0,
1,
0, 1.
0, 0, 1. So you can see A3 will give you a single output. Now this single output, we have used 4 cases altogether. So this is the first case output, second case output, third case output, fourth case output. So if I just track down this particular logic operation from here. So for 0, 0, we got an output of 1. For 0, 1, got an output of 0, 0 and 1. So now tell me, what is the logic gate operation that we have got from here? What could be the logic gate operation?
XR.
No.
In terms of option, what X or
XNOR truth
X.
table.
XNOR? Yes. So this is a truth table of XNOR. So therefore you can see that this A3 will give you the flavor of an XNOR gate. So this whole neural network is basically correspond to a XNOR family. So in this way, you can propagate these values one at a time. That is there in the solution sheet as well. If you have seen the NPTEL solutions sheet, you will see that they have first fed 0, 0 and then they have checked the output, then fed 0, 1, then checked output. That you can do. Otherwise, you can do the whole thing at a single time. So all the multiplication you can consider at a single time, and then you can get the final output. So that is what we are doing here. Okay. So any confusion in this particular question?
No, sir.
Okay. Okay, so with this, we have covered the week 5 quiz, and let us take some question regarding PCA and autoencoder for week 6 quiz. So what is the which of the following is the false statement about PCA and autoencoder? So which one is basically corresponds to nonlinear operations out of PCA and autoencoder? Which is a nonlinear operation?
Autoencoders.
Yeah, autoencoder is a nonlinear operation. So let us scan through this option. So PCA works well on nonlinear data. So first option is incorrect because PCA is linear. So PCA works well on linear data, but autoencoder are the best for linear data. So this is incorrect. Autoencoder is best for linear data as well as it gives good result in case of nonlinear data as well. However, PCA gives good result in linear approximation. In case of nonlinear approximation, it is not able to track down good representation. Okay, output of both PCA and autoencoder is lossy. Yes, that is true. For example, uh, you have seen in the week lecture slide. So let's say you have a data like this. Your PCA, your PCA gives an approximation like this, and let's say your autoencoder can give an output like this. So you can see that there is a still some loss of data is there because you are representing a higher dimensional data using a lower dimensional data. So there will be some loss, but we try to reduce the loss as far as possible. Okay. Both PCA and autoencoder can be used for so this one is correct. So both PCA and autoencoder can be used for dimensionality reduction. This is also correct because we use PCA and autoencoder to represent a higher dimensional data into lower dimensional space. So therefore, these two are correct options, and this is the false statement. So the option A is the false statement. Okay. So in the next question, it is given as given a input X linear autoencoder, they have no bias. Okay, with random weights W for encoder and W dash for decoder. What is the mathematical form to get the optimized weights? So in an autoencoder, what we have, what is the structure of an autoencoder? What are the layers that we have? Anyone? Yes, anyone? What is this layer called?
Bottleneck.
Hidden leg.
This is called bottleneck layer. And this is your output. You can write it as X hat. So you try to deconstruct the output, and this is your bottleneck. Okay. And what is the loss? Loss function? So one loss is data loss, one loss is regularizer. So data loss is basically given this input X, we try to generate the X hat at the decoder side from the bottleneck representation, and we try to minimize the data loss by using some sort of distance matrix. It could be an L2 loss, it could be an L1 loss. So in this particular question, in each and every case, people they have given the representation of L1 loss, that means absolute loss. So let us consider the absolute loss only. So the absolute loss could be X hat minus X, or you can write X minus X hat, because anyway they will give you the same result because you are taking the absolute value. So whatever component you take first, put it at the first position, it doesn't matter actually. Okay. So how what and let us consider this is this part is called what in the autoencoder? What is this part called?
The encoder.
This is called encoder. And the encoder has weight W. And what is this part called?
Decoder.
Decoder. So decoder has weight W hat or W dash. So to get X dash, what will be the equation? What will be the equation to get X hat? Let us consider the bottleneck is represented as B. So how we can get X hat? Okay, so let us consider the X hat is coming from B. So you have B, you have weight over here, and then you do the matrix multiplication in between B and W, then you will get X dash. So that means it is W multiplied with B. Now how you can get B? You have input, you have encoder weights. So you multiply input with this encoder weight, then you will get B. So therefore W dash W, and then you can write X over here. So this is how you can get the what you call the final output. So you can just replace this thing over here, W dash W into X. So this is the loss, and you can check that this is the final correct answer. So in terms of mathematical operation, whenever you will be given any neural network problem, just think it as in terms of the matrix multiplication problem. You start with this operation. For example, if I again if any confusion is there in this particular operation, you can just think in terms of feed forward network. Again, feed forward concept. So in the feed forward concept, first output is the bottleneck output. So bottleneck is basically W into X. You have W, you have X, you take W into X, you will get the bottleneck output. Then again use feed forward concept. From B you are getting X dash. Now how you are getting X dash? That is W dash into B, and then you just replace the value W dash W into X. So from this you can get the loss. So option A is the correct one. Any confusion in this particular question?
No, sir.
Okay. Okay, so the next question states that a single hidden and no bias autoencoder has 500 inputs. So whenever these kind of questions are there, first try to draw or visualize the neural network architecture. So you have 500 neurons in the first layer, then you have 100 hidden neurons, and this is the autoencoder. And you have single hidden layer. Hidden layer has 100 neurons. So over here you have 100 neurons. So this will form the encoder part. So at the decoder, what will be the how many number of neurons we will have at the decoder side? At the decoder side, what will be the number of neurons in the decoder layer, decoder output layer?
500.
Yeah. So you will have 500 neurons. Okay. So this is decoder. Now you need to calculate the parameters associated with this particular whole autoencoder network. So again, if you need to find the number of parameters, again think the problem in terms of a matrix representation. So let us consider this is W encoder and this is W decoder weight. So what will be the shape of W encoder? Just think it in terms of matrix multiplication. What will be the shape of W encoder? Is anyone?
500 into 100.
Yeah, so 500 into 100. And in case of decoder?
100 into 500.
Yeah, so 100 into 500. Sorry, 500. So total number of parameter in case of WE, parameter in case of WE will be 50000, and WD will also be 50000. So just take total number of parameter is WE plus WD will be 00010. So this is the total number of parameter for this particular autoencoder architecture. So this is same as what we did or what you have did in the last quiz as well. In case of last quiz, they have asked about some MLPNN architecture. Now the same thing you can see that we are doing in case of autoencoder architecture. Just think the problem in terms of matrix multiplication and then you can get the correct answer. That's it. Okay. So you have given the sigmoid function S as sigma of x. So what is the functional representation of sigmoid function? 1 divided by 1 plus
e to the power minus x.
yeah, e to the power minus x. So let us just do some numerical operations. So the question states that you have tan h function t, you have sigmoid function x, and what is the relationship between t and s? So s multiplied with 1 e to the power minus x is equal to 1. So I can write that s plus s into e to the power minus x is equals to 1. So s into e to the power minus x is equals to 1 minus s, and then I can write 1 minus s by s. Okay. Now, what is the formula for tan h?
1 minus e power minus 2x by
1 minus
e to the power minus 2x
e to the power minus 2x
by 1 plus e to the power minus 2x. 1 plus down.
1 plus e to the power minus 2x. So now tan hx is given as t, and then 1 minus e to the power minus x representation we already have, and I can write it as in this format, e to the power minus x whole squared again. And now you just put this particular thing over here, 1 minus s divided by s whole square divided by 1 plus 1 minus s by s whole square. And then you just simplify it, you will get the final answer. So I'm not doing the mathematical calculations, you can do it by yourself. So if the main concept is clear, right? Or if you have any confusion, I can still clarify. Any confusion in this particular question?
No, sir.
Okay, so you just simplify this solution, this particular form, you will get to the final answer accordingly. Okay, so moving to the next question. So the next question is about the principal components. So they have given two vectors. Two vectors have been given in each of the cases, and they are asking that which of the following two vectors can form the first two principal components. So what are the properties of principal components? Anyone? What are the properties of principal component?
They are orthogonal.
Yeah, they are orthogonal basically. And why they are orthogonal? Any reasoning for that? Principal component are basically the eigenvectors, and these eigenvectors are collected from covariance matrix. Covariance matrix. And generally this covariance matrix, these particular covariance matrix are symmetric, and these covariance matrix are square matrix as well. So this is n cross n. So they are square matrix, symmetric matrix, and for any symmetric matrix, if you evaluate the eigenvectors, they are orthogonal to each other. So that is the reasoning for that. So the eigenvectors or the principal components are basically the eigenvectors which are basically computed from the covariance matrix. As the covariance matrix is symmetric matrix, for symmetric matrix, the eigenvectors will be orthogonal. So this is the reason why principal components are orthogonal to each other. Now, how to check two vectors are orthogonal to each other? How can we check? If two vectors A and B are given, how can we check that they are orthogonal to each other? Yes, anyone? Okay. So let us consider you have the unit vectors I cap and j cap. They are orthogonal to each other. What is the dot product value between I cap and j cap? Yes, anyone? What is the dot product value between I cap and j cap?
0.
0.
Zero.
So how? Yeah, so 0. So this is mod I cap, mod j cap, and cos 90. So cos 90 is 0. So therefore the value is 0. So you can see the dot product between two vectors should be 0 to ensure that the vectors are orthogonal to each other, right? So you have to check that whether the dot products are 0 or not. So let us consider, let us first check option A. So your A is 231 and B is 319. What will be the what will be the dot product result?
0.
Yeah, 0. So 3 to the
6 plus 3 plus 9 minus 9.
this is orthogonal, as because dot product of A and B are 0, so they are orthogonal. They can be eigenvector and they are forming the principal components, because principal components should be orthogonal to each other, and they are, and option A is satisfying that rule. Let us let us again check for option B. So in case of option B, the dot product result will be -4 +4 and -8. So you can see that the dot product result is -8. That means non-orthogonal. So in other cases also you will check that the dot product for any of these vectors are not equal to 0. So and as these are not equal to 0, this cannot form the orthogonal set of pairs. And if they are not orthogonal set of pairs, then they are not the principal components. However, in option A, you can see that dot product is 0, which ensures that they are orthogonal and which also ensures that they are the principal components. So any query in this particular question?
No, sir.
Okay. So with this, we have completed the practice questions for week 6 as well. So if you have any query, then I can take it up. Otherwise, we can stop the session here. If you have any further queries, then I can take. Otherwise, we'll
Sir,
stop the
in
session.
assignment 6, there are few questions like from 5 to 8 or all are of similar type. What is the strategy we have to apply, sir?
In the current that is live, the quiz
Yeah,
that
yeah.
is live you're asking about,
Yeah.
I have not seen. So you can post your question there. I have to check because I have not checked the questions for this particular quiz. So if you raise your question over there, I can give you some hint in the chat, in the forum, because I also haven't checked the questions yet. So what are these questions about? So as you are saying, they are similar. So which concept they are actually trying to convey over there?
These are two-layer neural networks, sir.
Okay.
But the weights given are in the form of a matrix. And like they have asked us to find A1, node A1 and A2.
So you can use, probably you can use this strategy. So over here you can see I have also used the matrix representation of the weights. So you can process your data, or you can process the input data using a matrix multiplication.
This correct, sir. We can apply this strategy, but they have given J cap also. So where to use the J cap, sir, here? Sorry, J dot.
J dot, that means loss function, right?
Yeah.
So we have solved one question like that as well. Where is that one? Yes, this solved one question like that. Let me check this. Yeah, so over here you can see this is not the same thing. They have given probably two-layer neural network, and over here we just have single neuron. So what you have to do is that you have to get the output. Then from the output, you need to take the derivative of the second last layer or first or the immediate last layer like that. So you can follow probably the neural network example of this particular week. You can use this week's lecture, because professor has illustrated some similar kind of concepts in this particular week. So are you talking about week 6 or week 7? So I think week 7 is also live.
Week
So
6, sir.
Okay, week 6. Okay, so for week 6, probably you can see these two lectures. So as you're talking about two-layer neural network, Professor PKB has also shown some examples of two-layer neural network and backpropagation, applying backpropagation over there in these two lectures. And he has taken some numerical problems as well. So I think you can refer to these two lectures. So you will get to know that how to do the backpropagation over there. And I think the questions are related to backpropagation only.
Okay, sir.
Okay, so you can post the question. I can give you some hint over there. Okay, so apart from this, any other query? Okay, so I hope no further query is there. So I think we can end this session here.
Okay, thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So you guys will be writing the exam, right?
Yes, sir.
Exam.
Yes, sir.
Okay.
Yes, sir.
Your exam is there?
Sir, one query regarding